All right, welcome back. Any questions about stuff before we get back into this section? All right, so we briefly got into this section where talk about another way to look at this closest vector problem. So if given a basis of a subspace and some arbitrary vector, can you find the vector in that span that's closest to the vector that you care about? So in 6.2, we talked about this process of using dot products to make that happen. Basically, what we're doing here is we're answering a similar question, except now we'd like to use a more traditional matrix approach. One that requires, pretty much everything we did the last 2 days required a lot of hand calculations. Hopefully this can be a little more automated. So where we ended last time was this relationship here. So to kind of reset the stage, what are P and U? P is some vector that's spanned by the vectors that make up this matrix A. And U is the vector that I'm trying to minimize my distance to, the thing I'm trying to get the closest to. What vector A is, and all these other modifications are based on, vector A is the matrix that contains all the basis vectors, of which P is spanned by. So basically all we've done in this section so far is kind of develop where this thing comes from. Now we can use it. So here's my vector V that I'm trying to, basically I want to know this. What is my closest vector in the span of W? Of the infinite number of vectors that are included in the span of W, which one comes the closest to V? So what's my matrix calculation I'm doing here? So A times A transpose. Is that it? My memory is failing me. There was another A transpose. Okay. So like we said last time, how many different matrices do I have to deal with to make this calculation? Just the one. Because there's A transpose, there's A transpose times A, and then there's the inverse. There's a lot of different things that are going to be involved here, but they're all based on A. So as long as we define A and U, really, you can basically put that in your calculator and get what you want pretty quickly. So to build what A is, we should really know what A represents. So again, what does A represent in this calculation? Yeah, basically it's those basis vectors. So the columns of A are going to be the vectors that belong to the basis of the subspace that I'm interested in. So this is what A is. And U is, let's just make this easier. Let's call this thing V. Since I called it V, I'm trying to find the thing that spanned by A that comes closest to V. So I admit I have not tried this on a TI calculator. I know in MATLAB you can fire this all off in one shot and it works. Let's find out if your calculators can do that. The only thing I would really, really caution you about is that the parentheses really need to be around this. If you don't do that, your calculator will just try to calculate everything from left to right. So while you're doing that, I'm going to write out long form what is actually happening. So there's A times A transpose. The thing to do this calculation, you only have to define two matrices. Everything else can be a function of those. Let me know when you got something. Oh no. Did you put these parentheses in for around? Did you get something? Ooh. Ooh. 5.3 times 10 to the 13th. To the negative 13. That could be okay. So that's your first entry? Okay, I actually feel okay about that. Here's how I feel about that top number though. What is 5.3 times 10 to the negative 13th? It's sometimes your TI calculator will it's looking for zero. I mean it's less than a trillion of something. Does this answer make sense?
Yes.
Why are you saying it makes sense?
Well, 0 is supposed to be 1, 11 is supposed to be 12, 8 is supposed to be.
Where those are all, I mean, you should wind up with something that's reasonably close to the thing that you were trying to project onto. If we were going to get really deep in the theory, we could prove that no other vector in this span it comes closer than this. We're not going to do that, but that's kind of one small check you can do. Did the vector you wind up with approximate the thing you were trying to project onto? So in this case, it approximates V pretty well. If we were to do the Pythagorean theorem on that, we get the square root of 3. We're off by square root of 3 units. Since at least, yeah, so I want to make sure we have the keystrokes down though to do this in your calculator. So walk me through how you did this.
I had to do it in parts.
You did have to do it in parts?
Yeah, well, so I took the first parentheses.
Okay.
And I plugged those in, and I multiplied with the A in front.
Okay. Okay. So instead of, okay, so I'm assuming first you defined A, right? So define A and V in, is that the math and then matrix menu? Okay. Was anybody able to get that in one command line, in one line? Okay. Oh, you can't, so you can't write A and then, okay, that's good to know. So A and then,
Yeah, that did fix it.
that did?
Yeah.
Cool. So I think if you, okay, so I'll make sure that I'm writing the keys now. So A asterisk. How do you do the transpose of a matrix?
So you put
Okay. So put A first and then do the transpose. Then call A again.
Yeah.
Oh, good call. No matter how many times MATLAB yells at me to do that, I'm going to forget again. Then do you do inverse after this multiplication? Okay, spilling onto another line. Awesome. And I assume that inverse is back in the same menu the transpose is in? Or you, okay, either one works. All right, then multiply again times, I assume I would have to, oh, you don't? Okay, also it transposes first if I just do that. Okay. Ooh. A lot of keys, still would rather do this than deal with it by hand. And then whatever you called V, probably V. Here's the nice thing though. If we need to do this again, and we're going to do it again very shortly, you should just be able to redefine your matrices. And then on a TI calculator, how do you like cycle through your old commands? Okay. So if you just hit up until you get back to this string of commands, you shouldn't have to type it in from scratch again. Do you agree with that? Okay. Cool. Any questions about A, the mathematics behind how this works, or B, the process of how you make the calculator do this for you? And TI calculator is really useful as long as you tell it exactly what you want it to do. If you're off by a little bit, I think in the last 40 years, they've gotten no better at telling you and helping you fix whatever the syntax errors are. Questions first, can we move on? Okay, let's make sure that I was right about whether you can just reuse that command. So I'm essentially asking the same question here. I have the basis vectors for a subspace. I have a vector I'm trying to find the projection, the orthogonal projection onto. So what can you change with what we just did to answer this question? Okay, so I'm assuming you're calling them A and B. What is A this time?
I would still do the matrix.
Okay, so now it's this 4x2 thing. And I think if what we just did was based on A and B, I think you still have to put the vector as B and the basis, the columns of the basis as A. Otherwise, you will have to rewrite that command that comes later. So yeah, let's verify. I think after you update what A and B are called, you should be able to just recycle that old command and get what you want.
Down to 18.
218.
11.
Okay. That doesn't feel very close, but actually, it might be okay. I'm spanning 4-dimensional vectors, right? and I only have 2 vectors in my basis to do that. So the span is probably not very, it's probably not a good representation of R4. So as opposed to, what did we just do? We just did 2 vectors to span 3 dimensions. We're probably better equipped to do that than we are to do this. So hopefully it makes sense that we're off by as much as we're off by. So for this one, each coordinate or each entry was off by exactly 1, right? How wrong are we here? By at least 18. And then as much as 22. But I still think we're correct. If we had a third vector in here that was linearly independent to increase the span of this basis, I think we'd get closer. Questions? Okay. So yeah, rely heavily on your calculator for this. But remember that we're basically the thing we're asking it to do is this. So just in case you get to a point where you do a bunch of other stuff and that command gets buried, I don't know if there's a way to save command lines. That doesn't sound like something I remember being able to do. But as long as you can, recreate this command, you'll be fine. All right, so let's ask the question a little differently. So instead of giving a basis instead of using your vectors, your basis as vectors, now I'm describing the span as a plane. If you haven't taken Calc 3, you might not know what a plane is. Basically, a plane it's a flat surface. So, can I pick this up? Nope, that's all attached. But like, think about the flat side of this as a plane. So there are 3 dimensions here, right? X1, X2, X3. Basically, a plane is just like a flat, infinitely long sheet that extends in all directions. So it's a 2-dimensional thing that lives in 3D space. A good analogy is a straight line. A straight line is a thing that exists in 2 dimensions, even though it itself only has 1 dimension to it. So it can basically this plane will only encompass a small portion of the vectors that make up R3. But the method we're talking about doesn't really work with objects like this. It only works if I have some basis vectors that I can turn into a matrix. So are we able to do that? Can I turn the plane that's given this equation, I should call this, I put a colon here. Can I turn this equation into some basis vectors? How so? How would you do that? If I divide everything by 3, I get x1 minus a third x2 minus x3 equals 0. Okay. Okay, so isolate x1. So x1 equals a third x2 plus x3. Does this look like something we've done now? So now I would like to eventually turn this into some basis vectors, but how do we get there? Let's write a generic x1, x2, x3. If we're going to parameterize this, how many parameters do I need? 2. So I isolated x1, so I'm calling that my lead. So if x2 and x3 are parameters, what does our top row look like? What does x1 equal to? 1/3, 1. X2 is equal to itself. And then X3 is also equal to itself. So from there, can I build a new matrix A? What's it going to look like?
1/3, 1.
Right. So basically stitch those two column vectors together to make this 3x2 matrix. And then we care about what B is as well, but that was given to us. 21, 19, 21. So now we're back to the place where we were when we went to our calculator for the last couple of examples. So you should be able to recycle that command again. So that doesn't seem right. Is that it? Yeah, okay. All right. And this U, or actually I'm calling that B. Whenever you have something, let me know. 24, 18, 18. Sounds reasonable. So again, we're back to a fewer dimensions in space. For every example we've done, we've only had 2 vectors in our basis. But with fewer dimensions, we should be able to get closer to any given vector. How are we doing? Okay. Questions about this process? Okay. So let's go ahead and stop here. All right. So next thing we're going to talk about is this idea of least squares solutions. So before we talk about what that even means, let's try to answer this question. So if I give you a system of equations, can we find a solution for it? Is this something we can do? How so? Okay, what would the matrix look like? Two. Right, so can make an augmented matrix out of this because let's also write down the not the unaugmented version of it. 1, 2, 1, 1, 2, 1 times xy equals 4, 5, 1. So now that we have this augmented matrix, what could we do to it? Yeah, so if we reduce that, so right now I'm not asking what the solutions are, I'm asking just if we can solve it. So the reduced row echelon form of that augmented matrix should give us all the evidence we need. So whenever you got a reduced matrix, you got the identity. Okay, so 1, 0, 0, 0, 1, 0. So what does that mean for us? There is no solution, right? But it would be nice if we can do something better than that. So this has no solutions. So in linear algebra, we call this an overdetermined system because we have more equations than unknowns. So basically what I could do, I could probably ignore, or not probably, these are all linearly independent, right? Can we say that now based on what we know? If we reduce it to the identity, then we know that these three equations are all linearly independent. I know that I could ignore any one of them and get a solution that would like actually fit the two equations I'm looking at. But our matrix shows that we can't satisfy all three of them. So what we'd like to do instead, we would like to find we want to find the best solution. We can't find the ideal solution, but we want to find the best one. How close can we get to 451? So hopefully even though this is like a different setup, different context, hopefully the question we're trying to answer feels a little bit familiar. So I can't reach the thing I want to reach, but I want to know how close I can come to it. We could do something extremely similar. So similar, I'm not going to redevelop it for you. One thing I will point out here is this is different from the thing we just looked at. Do you notice how? There's no first A. Why not? So let me write down the thing we just looked at. The thing we just looked at was like this. It was vector P equals A times A transpose A inverse times A transpose B. Or I think I was calling it U. So why do these look different? So let's flash back to our previous section. What kinds of things are P and U? Yeah, they're both vectors, but what do those vectors represent? So in our last section, P was a vector that was in the span of the column space of A, right? So the way we get P is to multiply that matrix A by some column vector made out of its coordinates. So that's why we had that extra A in our last section, is because the thing that was on the left-hand side of our equal sign was, we were just calling it P, but it really, where it came from was the product of matrix A times vector C. But now what are we trying to find? This X tilde right here, what kinds of things live in this X tilde? I'm gonna go look back at this previous slide as an example. So like the thing I want to find is this X tilde. What will be in there? Right, it'll be my best X and Y pair that get there. And that's what X and Y are. I'm not going to multiply those by some other matrix to get a new object. In this case, the thing I want is simply that vector. So that's why this form is missing this initial matrix A out front. So to be clear here, let's do this. Let's do A inverse on the left on both sides here. That's going to cancel that out. And then if I'm saying P is equal to AC, then A inverse P is equal to A inverse AC, which is just C. So if I do that inverse multiplication on the left, and now these things are essentially identical, except the fact that I'm calling C and P different things. So just to recap, process is very similar. The thing I want, the thing I'm chasing down is pretty fundamentally different. Questions on that? So now that we've talked about that, can we find the best solution to this system of equations? We know the thing we find is not going to be 4, 5, 1. Or sorry, we're not looking for 4, 5, 1 at all. We're looking for what x1 and x2 are. So based on our calculation, or the calculation we're going to do, we need to define a couple of things here. We need to define A and B again. So what's our A going to be?
One, two,
And where'd you get that? Right. So, and just to drive that point home even further, if we look at the left-hand side of our augmented matrix, those are the coefficients of x and y, which I'm now calling x1 and x2, but still, they're two variables. They're two unknowns that I'm trying to identify. And then what's B going to be? 4, 5, 1. So the thing I'm trying to find is this x tilde, my approximate least squares solution to x, which is going to be A transpose A inverse times A transpose B. Let's hope we get something reasonable. What should the order be of the product you get? 2 by 1, because I'm looking for x and y. All right, how did we do? Negative 4 over 11 and 29 over 11. Is that good? Is that close? I have no idea. How could we figure out if that's like good at all? All right, let's just look at it. So if I plug these into my first equation, I get negative 4 over 11 plus 58 over 11. That's what, 54 over 11? That's a little bit less than 5. Or negative 4 over 11 plus 29 over 11. That's 25 over 11. It's about 2.5. And then 2 times negative 4 over 11. So about how far off are we? So 54 over 11, that's like just a shade less than 5, right? 4.9. This is about 2.4. And this is 1.9. So they're not terribly far off. The middle one, the middle equation is the worst, but we're trying to find something that comes close to satisfying all three. Questions about how this works, the result we got? So what's the actual answer to this thing I asked? Like, what is the least square solution to the following, not equation, to the following system? That is this technically is not what we were looking for. I did this to kind of show that what we found was good. But let me ask it this way: when you're solving an equation, what do you actually like? What's the thing you're after? What's the thing you're trying to get? What's that? I want to know what the variables equal. And that came from this. This is what x1 and x2 are. Or approximately what they are. That's as close as I could get to a good pair of x1 and x2 that actually approximates all those equations. This was more to illustrate that this got us pretty close. So questions here. Does it seem similar to what we did in the last section? Okay. So yeah, I mean, the process is very similar. The calculation, basically this thing that you ask your calculator to do is going to be very similar. The biggest difference lies in the fact that we're now looking for something different. So in the previous section, we were not just looking for the coordinates for some basis. We were looking for the coordinates to some basis. We want to multiply that by the basis to get a vector. Now we're just looking for the coordinates of x1 and x2. Let's go again. Tell me what to do. Okay. What does the A matrix look like? Okay. Yep. Yep. Okay. So again, the coordinates of all of our variables in order. And then B is going to be and just like last time, you should be able to, after you redefine A and B, you should be able to reuse the command we just used. And what's the order of the thing I should be expecting to get out of this? 3 by 1. -8, -5, +5. Is that good?
Yeah.
We don't know. So we could find out if we're even close. That is the wrong symbol, not hat, tilde. Yeah, they mean different things. 72 plus 25 minus 15. It's about what, 82? First equation seems okay. Seems close. Do we have a way of finding out how close our answers got? Plug them into what?
Original system.
Yeah, then we have to calculate those by hand. I don't want to do that. Yeah, if you want to redefine it, or basically, I think if you do on your calculator, A star ants, as long as this was the last thing that you got, I think that will just give you, that should give you a 4 by 1 matrix or a vector that hopefully all of those numbers should be close to. I did the first one and I got 82. So if I did that right, you should have got 82. Yeah, when someone has the other three, let us know. Okay. So a couple of our coordinates are pretty off. Actually, it's just one that's like off by a lot. But still, I think this sounds good. The solution feels like it's close. How we doing? Okay. That's all of that. Quick section. Let's just take the final tomorrow. Where we at right now? See if I can get this done before the Diamondbacks trade the rest of their team. All right. So last thing I want to go over in chapter 6 is this. Something I'm guessing a lot of you have probably done before, or at least seen, but maybe not done on your own. So it's related to what we just did, but basically, if I give you an overdetermined system of equations, so I give you more data than is needed to actually solve, there's a chance that you will not be able to satisfy everything. So let's look at kind of a common occurrence of that. So I would like to come up with a straight line that meets all the points I'm showing you. Is that possible? Clearly not possible. But instead of saying, oh, it can't be done, we can try to find something close. So how could we do that? Right? We're going to find a regression line, right? Is that something you've ever done on your own, or is it something I'm guessing a lot of you have asked Excel to just spit those out for you, or MATLAB. Like you can give it some points and say, give me the line of best fit, and it'll give it to you. But have you ever calculated it on your own? Okay. Do you remember how it works? Okay. So let's kind of piece it together based on things we've already done. So hopefully if I get a straight line, it's going to look something like, I think hopefully if I draw you that's awful. But if I can draw something that, yeah, that's perfect. I mean, our answer should be something like this, right? But we can be really, really exact. I mean, we're not going to be exact. We can find the least bad thing. So that's what we're going to do. So if I want to try to find a straight line that fits all of those things, I would like to find the equation of a straight line. What does the equation of a straight line look like? Y equals mx plus b. So I would like to find an equation of a thing that looks like this. What do I need? So what do I need to know about these symbols to be done? Like, what do I need to define here to get a straight line? Slope is one of them, right? Which one of these 4 letters stands for slope? M. And what else do I need to find out? Y-intercept, and that's what B is, right? What are Y and X in this scenario? Those are all of these, right? So I don't need to find values for X and Y. Those are the things I need to let vary. But M and B are constants. If I figure out what they are, then I have what I want. So here's what I can do. I can rewrite all of these 5 things as, kind of fit them into this form. So let's go from the bottom up. Negative 8, negative 29. Well, that means that negative 29 equals negative 8m plus b. So it probably seems like a really backwards way of looking at the equation of a straight line, but is what I'm writing down sensible? So here's the game now. Instead of looking for X and Y, I am telling you a bunch of things that X and Y are equal to. And I want the M and B that are going to give me the best shot of approximating. 17 equals 9m plus b, and 19 equals 8m plus b. Can I redefine this as a matrix somehow? Augmented matrix. What would the size, what would the order of that augmented matrix be? 5 by 3. So 5 rows. Actually, let's do that. Let's not jump straight to the augmented matrix. So if you're saying an augmented matrix, I'm assuming that we have a 5 by 2 matrix multiplied by what order of another matrix? 2 by 1. So this is a 5 by 2. Why is it 5 by 2? What's that? Right. So okay. So the answer vector, what's the order of that one going to be? 5 by 1. So this is the equation we're setting up. So hopefully this calculation works, right? 5 by 2 times a 2 by 1 yields a 5 by 1. Okay. What are we trying to find out? What are the things we're trying to find values of? M and B. So I believe the 2 by 1 matrix should contain M and B. That's the thing we're after. So what goes in this 5 by 2? Not quite. So that's why I wanted to fill in the M and B first, because the fact that I'm multiplying by this 2 by 1 that has M and B in it, this will dictate what has to go in here and how. So what's the top row going to look like if I base it on this top equation? -8 and what? There are -8 m's and 1 b. So what's the next equation or next row? -5, 1. So I'm just going to get this out of the way. In every one of these equations, I am dealing with a single y-intercept plus b. So the only thing that varies is the left-hand column, which is whatever the coefficient is of m. And then what goes in this 5 by 1 matrix on the right-hand side of the equal sign? -29, 3. And hopefully we can see that this matrix equation on the bottom matches the list of more traditional equations on the top. So if I multiply this top row by this column, I get -8 plus 1b. Sorry, -8m plus 1b equals the top row of this vector. So hopefully this structure fits. So now how do I solve for m and b? Yeah, basically we're looking for a least squares approach again. It's just, and it is exactly the same as the least squares approach we just did, except I'm not looking for x1 and x2. I'm not looking for, strictly speaking, I'm not trying to solve for variables. I'm trying to solve for constants whose values I don't know. So this vector MB is going to be equal to, equal to A transpose A inverse A transpose B, where this is A, this is B. What do you expect M and B to look like unless you've already gotten there? What's that? M better be positive, and it better be like relatively large, I would think, right? What about B? I would negative, probably not very negative though. Does anybody have values yet? That's fine. I mean, then ooh, yeah, let's go decimals. Cool. Negative 4.147. Nah, I'm not gonna do that. That's fine. Are these numbers logical based on what we were trying to do with them? So y-intercept of, I don't know, there. Slope of about 3. Go away, menu. Yeah, that feels, those numbers feel okay for the data we were giving it. So even with my rounded up slope of 3, it still feels reasonable. So what's the difference between this and what we just did in the last section we just flew through? Not much, right? In terms of the what, like literally what you asked your calculator to do, I'm guessing you probably could have just used the same command you just did. The biggest difference is how we're constructing the matrices that we're feeding into it. Because now I'm not trying to find out what I'm not trying to find out what variables like I'm not trying to find what x and y are equal to. That is the thing I know this time. Like we didn't talk about it, but if we look back at the system's equation, would just look like we knew all the coefficients. We knew all the constant coefficients. Now the things we know are a few samples of the variables. And we're trying to make those coefficients match up. So really we're looking for slightly different things in the exact same way. Questions? What if it's not a straight line? What if I want to find a parabola that best fits a bunch of points? How does that change what we just did? Right. So we know what the equations of straight lines look like. They are y equals mx plus b. So we can start with the most general version of this thing. What do equations of parabolas look like? Y equals x squared. Is that as general as we can be? What kinds of equations make parabolas if you graph them? Quadratics, right? So this is a quadratic, right? Y equals x squared. But let's think about in general, what terms can quadratics have in them? I mean, I think they have to have an x squared term, right? But does it have to look exactly like x squared? Could it be negative x squared or 5x squared? Basically, it could be any multiple of x squared, right? Is this as general as we can be? So far, here's what I think we have. I think y equals ax squared. That's all the parabolas that look like this. What's the quadratic formula? What do you mean? You're on the right track, but there's, yeah. What do you mean by that? X equals, yeah, what's the quadratic formula? Let's write that down. X equals negative b all over 2a. Does the quadratic formula work for any quadratic you can think of? It should work for every single quadratic, which means that if I know what a, b, and c are, I should be able to use it, right? In general, like, where do we get those values a, b, and c when we fill out the quadratic formula? So basically, if we want to get as general as possible, all quadratics look like this, right? There must be an x squared term. And there might not be a bx term or a c term, but there might be. So if I want to be as general and like accepting as possible, because I have no idea what this parabola is going to look like, I should allow for the fact that all three of these things are there. So I want to pause there. I want to make sure we're okay on the rationale of why this is the thing we're fitting to and not something more specific. We okay with this? All right, now we got to build a matrix out of this. So how do we do that? How do we do it for the line? Okay, got all of our points. I got 4 points this time. They're a little smaller. Can you see them well enough? Let's pretend you can't. -2, 25, 0, 5, 562. I'm right here, and they look small to me. So I got 4 points. How am I going to translate these things into things that a matrix can deal with and help us make calculations on? Right. So how would I apply that? Let's go left to right. How would I apply that to this point here? A times -2 squared. Right. And one thing I should have asked a bit ago is, if we're going to find the parabola of best fit, when we get done, what are the things that we want to have found? What do we need to be looking for? A, B, and C. So when I start filling out this list of equations here, the only things that can be unknown are A, B, and C. So 25 equals 4A minus 2B plus C. Let's go from there. What does 0, 5 give us? 5 equals C. 0A plus 0B plus C. How about 62 and 5? Or 562, sorry.
Equals 25A minus or plus 5B plus
25A plus 5B plus C. And finally, 165 equals 64A plus 8B plus C. So to kind of recap, we wrote down the most general looking version of the kind of curve we're trying to fit to. Then we rewrote all of our data points in that form. What's a good matrix to, or we need 2 matrices. I'm reusing letters. I hope you're okay with that. So what are our matrices A and B going to be? Maybe it makes more sense if we do this. Here's the equation we're solving. Some matrix that I have to fill in times a matrix of the things we're trying to learn, which we said is ABC, equals some other matrix with values we have to fill in. So I think maybe the most logical place to start if we're trying to get our bearings is, what does this middle matrix look like? What are the unknowns? What are the things we want to solve for? If I'm going to multiply the matrix on the left by that column ABC, then what does a row look like? 4, negative 2, 1. How'd you get those numbers? Right. So those are the coefficients of A, B, and C. Which means another good row is what? 0, 0, 1, 25, 5, 1, 64, 8, 1. So those are the coefficients of A, B, and C, those 4 rows. What's the order of this matrix on the far left? 4 by 3 multiplied by a 3 by 1, which means this matrix on the right-hand side is a what? 4 by 1. So what are these 4 entries here?
25, 5, 2.
And let's be really clear, where do those numbers come from? Right. So those are like my y values. Those are the outputs of all my 4 parabolas, or my 4 data points. All right. So if this is the equation we're solving, even though I went from a straight line to a much different object, a parabola, and in doing that, I have matrices that are much different orders. Does our process still hold true? Can we still like just redefine matrices and fire off the same command?
Yeah.
Good. So the building blocks become different. The process, like the kind of the recipe, is still the same. So we're still going to do, so I want ABC, and that comes from, oh, I really hate that I'm reusing letters. Let's just call this question mark. Let's be lazy. A transpose A inverse times A transpose B. Based on what we know about parabolas, what should A be? Actually, should it be positive or negative? Let me ask it that way. Why should it be positive? It's a parabola that is oriented up. B is a little harder to ask about. What should be true about C? Why should it be positive? So I have, when x equals 0, I have a positive y-intercept. So as long as the other data points don't influence that in the other way, I would expect it to be small and positive. The effect of B on this is a little hard to isolate, so I don't know if we can make a prediction about that. Does anybody have a result yet? 2.934. Negative 3.538. 5.755. Do A and C match what we thought? Okay. So here's our parabola. 2.934 x squared minus 3.538x plus 5.755. How we doing? Okay. I think the next one might be a little bit involved for 5 minutes. So yeah, let's go ahead and pause there. So I'll wish you a happy weekend. I'll see y'all on Monday.